So this video covers section 12.3 in the 3D vectors chapter, and just a quick recap. We know that a unit vector is this length. It's just the vector divided by its length, and that little hat there shows that it's a unit vector of length 1. And if I want to find how to get from A to B, and I've got point A and point B, I can do point B minus point A, or I can work out the jump from A to B. So for example, if A was -2, 4, 12, and B was 0, -5, 8, then A to B, the easiest way of working it out is, well, what's the jump from A to B? Well, that goes up by 2, yeah, because I'm going from -2 to 0. The second one, the I, or the Y part, that goes from 4 to -5, so that's going down by 9. And the last one, going from 12 to 8, that goes down by 4. Okay, so that's a nice quick way of working out what we call a displacement vector, the vector that's taken us from point A to point B, and that one there is a quick way of doing it. So what we've got now in this section, there is no new stuff on vectors. It's about solving these geometric problems. So the first thing we're going to do is look at example 9, which is on page 344. And what we've got is we've got these 4 points, A, B, C, and D. And well, first of all, we need to find these vectors in part A to B, and we need to find D to C. Now we can use this quick method up here to do it. Let me just write down what A, B, C, and D are. And I'll just write them down like coordinates. So 2, -5, -8. Second one, 1, -7, -3. Then we've got, so it's gone down to there a bit. So 0, 15, -10, and then the last one is 2, 19, -20. Right, so if I want to find A to B, again, the quick way of doing it, what's the jump from A to B? So that goes down by 1, so -1. -5 to -7 goes down by 2. -8 to -3 is going up by 5, so there we go, this A to B. And we can write it in I, J, and K. We can write it as a column. I think in the question they say I, J, and K, so that would be something like -I, -2J, plus 5K, so it's easy enough. Last one, so we're going from D to C, so we're going from there to there, so that goes down by 2, so -2I. 19 going down to 15 is going down by 4, so that's going to be -4J. And then the last one, I'm going from -20 up to -10, so I'm going up by 10 on that one, so plus 10K. So there we go, we've got a nice quick way of doing it. So that's part A. Part B, show that the line AB and DC are parallel, and that DC is 2 lots of AB. Right, okay, if these are going to be parallel, then one's going to be a multiple of another. We did that in a previous video. So if I do that, so if I have a look, yes, basically this vector DC is basically this vector times by 2. So basically 2 lots of that vector equals that vector DC. So yes, they are parallel, yeah, because they're multiples of each other. This one is half of that, this one is double that, yeah, so there we go. So yes, they are parallel, and basically I've got that written down there, that expression that they wanted. And in part C, what they went, hence describe the quadrilateral. Well, what we've got is 2 parallel sides, but you can see that this one is twice as long as that one. So think of a quadrilateral, we've got 2 parallel sides. One side is twice as long as the other. Okay, it's going to be a trapezium. It can't be anything else. There are no other quadrilaterals where you've got parallel sides, one longer than the other, and they're parallel. It has to be a trapezium. Okay, let's move on to example 10. And in example 10, again, using this idea of the jump between points, it can make the question really easy. So we've got this quadrilateral, and it says that it forms a parallelogram. So let's draw a parallelogram. This is only a sketch. And these points are normally labelled in alphabetical order. So P, Q, R, S, like this. We want to find the coordinates of this point. So P is, I'm going to write it as a column just because of save a bit of space. So P is 4 minus 9 minus 3. Okay. Q is 7, negative 7, negative 7. R is 8, negative 2, negative 0. I reckon it's just 0. What's the point of negative 0? Right, what we know is the jump between the coordinates, because these sides are parallel and they're the same length, the jump between here and here is the same between the jump between here and here. Similarly, the jump that takes you from here to here is the same as this. So that makes it nice and easy. So if I work out a jump from here to here, basically the vector QR, I just apply it to this. So for example, what I can see is that the first number goes up by 1 as I go across from here to here. The second number, I'm going from minus 7 to minus 5 goes up. Sorry, minus 7 to minus 2 goes up by 5. And the last one goes from negative 7 to 0, goes up by 7. That means this does the same. Up by 1, up by 5, up by 7. So if I do that, what I'll get is 4 plus 1, 5. Negative 9 plus 5 minus 4. Minus 3 plus 7, 4. And here we go. We got the coordinate of S straight away. Or we could have said, how do we get from Q to P and work out what that is, and use the same jump to go from R to S. But whichever way you do it, you will get those answers for that one. Example number 11 is a nice straightforward one. It's just comparing coefficients. So this is the question here. Yeah, we need to find out what P, Q, and R are. Now, we just compare what's in front of the I, the J, the K on both sides. So here I've got 3 in front of I, I've got P in front of I, so that means that P equals 3 straight away. So I've got that, yeah, because 3 there, P there. Second one, I've got P plus 2 in front of J, and then I've got negative 2, negative Q here. So P plus Q equals negative 2. Which means that Q then is negative 5, yeah, because P is 3 there, plus 2 equals negative Q, so Q is negative 5. And then for the last one, I've got 120 here on that side, on the other side I've got P, Q and R, so 120 equals 4 PQR, so 120 equals 4, because that's P, or the 4's there, sorry, P is 3, Q is negative 5. So 4 times 3 is 12. 12 times negative 5 is negative 60. So negative 60, that means that R must be negative 2. So there's a nice straightforward one. Right, now example number 12 is a bit more of a challenge. Okay, so here we've got this cuboid like this. It's a fantastic cuboid there. We've got the lengths of some sides. We've got O, A, G, E, F, C, B, E, and D down, hiding in the bottom corner over there. Okay, we know that this is A here, and this is B here, and this is C here. Now, because it's a cuboid, all these parallel ones are going to be the same. That's going to be C. These ones in the back are going to be C. This is going to be B up here, so it's this one. Yeah, and that one down there, that's A. This is A as well. And that one is A, because we've got these lengths which are all the same sort of length, and they're parallel as well. Okay, so there's lots of stuff going on there. And what we want to do is to prove that the diagonals OE, so the diagonals OE and BG intersect. Okay, and basically we want to prove that where they intersect, intersect at, and let's call this point H, that's what they call in the question, and bisect, that was what was in the question. This is important. If they bisect, it means that they cut each other halfway. So if H is this point somewhere in the middle, then we want to prove basically that O to H is half of OE. And we also want to prove that B to H is half, that should be the other way around really. So half of OE is OH, yeah, they bisect, and half of BG is BH. This is what we want to prove, yeah? So the way we're going to do that, we're going to say, right, okay, let OH, yeah, equal some fraction. We're not going to put a half, we want to prove it's a half. So in the book they call it R, yeah, and basically we want to show that R is a half, and that it's half of OE, yeah, okay. Also, we want to show that the same with the other diagonal, that BH is also a fraction. Now we can't use the same letter because it may be we get different values. We can't assume they're the same. We need to show they're the same, show they're a half. They've used the letter S, again we want to show that's a half. Half of or a fraction of BG. Yeah, so think of R and S as these two things here. We want to show they're a half. That's what we're starting with. And the rest is just about finding roots from one place to another. Okay, now another way of getting from O to H, or we should have arrows there, O to H in my diagram, so O to that middle bit would be to go from O to B and then B to H. That's this point somewhere in the middle. So to get from O to H, I can go O to B first and then B to H. But we've said something about B to H, haven't we? B to H is this, a fraction of of BG. So we can write down, instead, we can write that as OH equals OB, yeah, along here, and then a fraction of BH, or a fraction of BG, so SBG. Okay, so we've got that so far. Now, we can do the same with going from, well, what we can do now, O to H, remember we said is a fraction of OE. So putting all of this together, OH we can replace with a fraction of OE, that equals O to B plus a fraction of BG. So all I've done is I've taken all the things that I've had and I've put them together into one statement. Now, O to E we can work out, yeah, because we can just go along the edges. So we can go there, there, there. In fact, it's A plus B plus C. So OE is just A plus B plus C, yeah, going along the edges of the cuboid. And O to B, well, that's just B. And B to G, so what I'm doing now is taking all of this stuff here. See, I've got OE is written as that, OB written as that, and B to G, again, I can just go along the edges. I might go backwards along one, but basically to get from B to G, I can go A plus C minus B. Okay. Now, what that gives me now, all of this can go into here, and what I'll get is ROE, which is that A plus B plus C equals O to B, which is just B, plus S lots of BG, A plus C minus B. Yeah, so it's all put together. And what we can do is we can compare the sides, what I have in terms of A, B's and C's. And if you solve them simultaneously, you will find that R equals S equals a half, which proves that they bisect because that goes right back to this bit at the beginning here.